Hello, my name is Krithika Manohar, and I will present kernel analog forecasting for multiscale problems. This is a kernel-based machine learning method for predicting data generated by dynamical systems. And it's work done along with my collaborators, Dmitry Birov and Andrew Stewart at Caltech, and Dimitri Giannakis at NYU Courant. If you'd like more information on this talk, please see the accompanying preprint on the archive. So I will begin with a little motivation for this problem. Why is purely data-driven forecasting challenging? Often we only have partial observations of a larger underlying dynamical system, and we have limited to no knowledge of the governing equations, which may further be nonlinear or chaotic, complicating our efforts to understand it. The data, in addition to being partially observed, may only be sampled at a macroscopic timescale. So we cannot hope to resolve what's happening at the microscopic timescales. For example, here we have sea surface temperature measurements of a larger underlying dynamical system, which consists of the subsurface and ocean dynamics, as well as atmospheric dynamics. And we would like to predict the El Nino index. The El Nino index is this average temperature of this band of ocean of the Southern Pacific. And we would like to predict it forward in time. And its deviation from the mean has been implicated in global climate and weather events. So it's very important to be able to predict this several weeks in advance. This particular example characterizes the challenges that we face. It is multiscale, it's nonlinear, it's chaotic, and the data is partially observed and sampled only at a macroscopic timescale, which is weekly in the case of the sea surface temperature fields. So with this in mind, I would like to give some background on analog forecasting methods in general. This was formulated originally by Lorenz in 1969. So we assume we're given time-ordered pairs of observations, which may be vector valued. In this case, you can think of it as the sea surface temperature fields, and responses, which are the values of the El Nino index, and we assume these are scalar valued. And we also assume we are given a desired lead time tau, at which we would like to know the response value in advance. So we assume that tau is a scalar multiple, integer multiple of the sampling time interval. And we assume we have q shifted values of the response corresponding to this integer multiplier. So given a new initial point x, we would like to predict the response forward by tau. Lorenz's idea was to basically find the observation in the training set that is closest to x in some metric, and find the analog of this point in the training set in the response set, and take the q-shifted value of the response and report that as your prediction. Now, there are several limitations with this approach. One being that it cannot handle chaotic dynamics. It is discontinuous in the lead time tau, which is not physical. And furthermore, we don't have an estimate of the confidence or the uncertainty associated with this prediction. Kernel analog forecasting is inspired by this approach, but in contrast of reporting a single value from the training set as your prediction, it weights all the given responses in your training set using a smooth kernel P. This kernel is constructed from a set of features, which I will describe later, that endow this prediction with some continuity. So this method is developed by Giannakis and collaborators who have proved that this prediction has an operator theoretic interpretation with respect to the underlying dynamical system. It's continuous in tau, the lead time, and we can estimate the uncertainty associated with a prediction. So for the first part of our talk, I'll go over kernel analog forecasting as well as some preliminaries on the math required to understand it, including the Koopman operator and reproducing kernel Hilbert spaces. And then I'll go over how to approximate the forecast from data. So for the purposes of KAF, we assume the underlying dynamical system evolves in the state space omega with possibly nonlinear flow map omega phi. And we assume also that the system is ergodic and equipped with an invariant measure mu. Associated with this dynamical system is an infinite dimensional space of square integrable observables in L2, square integrable with respect to the measure mu, and we assume that the responses Fn are outputs of this mapping from state space to L2, capital F. Given this setting, the Koopman operator is defined as the action on these L2 observables that composes them with the flow map, the dynamical flow map. And hence it advances these observables forward in time. Now in this space, although L2 is infinite dimensional, U tau is a linear operator acting on the space, and it gives this idea of a perfect forecast, which we want to approximate using KAF. And now the question is, how do we approximate its action from partial and finite dimensional observation data? And how do we map into this space and access capital F of omega tau? So to recap, we have a state space omega, which we cannot access. We do have access to observation data from the smooth observation map H from omega to X. And we have responses collected from the value of the observable from omega to L2. Now we want to build a map from H, that is data space, to U tau F. Now, Alexander and Giannakis showed that the optimal approximation to U tau F among all maps from the data to the responses is the conditional expectation, that is the expectation conditioned on the observations. This amounts to a projection of U tau F on a subspace induced by the observations. Now KAF approximates the conditional expectation in a data-driven subspace, which will be built in a reproducing kernel Hilbert space. And I will define that next. This predictor also has a consistency limit, as shown by Alexander and Giannakis, that in the limit of large data, as n goes to infinity, and then as the number of features goes to infinity, the predictor that we compute will converge, provably converges to the conditional expectation. We do this using RKHS machinery, which is provided by applying the kernel function on the observation data. Some quick background on RKHS is these spaces are explicitly constructed using the knowledge that every symmetric positive definite kernel function uniquely corresponds to an RKHS and vice versa. These spaces are characterized by the reproducing property, which means that evaluating a function in these spaces is given by the action of the kernel itself, which is very useful to have. And also we will be selecting a kernel that is not only a symmetric positive definite, but also is a Mercer kernel, so that the feature spaces associated with it is infinite dimensional. The algorithm itself is conceptually straightforward. In order to compute these features, phi and psi, we compute the eigendecomposition of an n by n symmetric positive definite kernel matrix that results from applying a kernel function, which I will mention later, pairwise on the data points x. Next, we form the projection of u tau f by expending u tau f in the basis of eigenmodes, which are the orthogonal eigenvectors of G. So this is, as you can see, Cj are the coefficients of this expansion. These are computed using this inner product of Vj composed with H and u tau f. Now the key idea is that we can evaluate this integral or approximate this integral by exploiting ergodicity and computing it by averaging this summand in time. So we can take all the collect all the values of Vj and the time shifted values of the responses, which are our approximations of u tau f, and sum over them. Now we can evaluate the predictor at a new data point x by mapping from Vj into the RKHS basis functions Psi-j using a procedure known as the Nystrom extension. This is essentially extending Vj's which only take values at the training points xn and evaluates them at a new point x via the action of the kernel. The resulting value of z tau of x is our approximation to the conditional expectation and therefore the forecast. The specific kernel we will use is a variant of the squared exponential kernel, or RBF kernel. We will use one with, instead of a scalar bandwidth, a variable bandwidth, which compensates for variations in the sampling density using data-dependent parameters, delta, which is a scalar bandwidth parameter, r, which is an estimate of the sampling density, and m, an estimate of the manifold dimension. These are computed all at once in a tuning procedure described by Berry and Harlem. Once we compute this kernel matrix, we perform a bistochastic normalization, which results in a symmetric positive definite kernel. Bistochastic because the rows and all the columns sum to 1. The reason we do this is that the resulting operator G approximates a diffusion operator on the manifold from which the data is sampled. So the eigenvectors have this additional interpretation as geometric harmonics over this manifold. So we normalize, and we never form G explicitly. Instead, we compute the eigenvectors of G using the left singular vectors of an intermediate matrix K hat. So just to summarize some of the advantages of KAF, the most computationally intensive step, the eigendecomposition of G, is only computed once. These features can then be reused to predict other observables, such as probabilities of events using indicator functions on your data, or the conditional variance of your prediction, which gives you confidence or estimate of uncertainty associated with your prediction. We compute this conditional variance as before, as we compute the conditional mean. An expansion in the RKHS basis functions, where now the coefficients are this inner product of Phi j composed with H and a new observable, which we assign as the ground truth value of the prediction at the training points minus the prediction at the training point squared. So this is an estimate of the conditional variance, same as how we computed the conditional expectation of the forecast before. So now that we have a way to predict the conditional mean and the variance, we will do an application to partially observed multiscale dynamical systems, which give a systematic way to predict and analyze the prediction in terms of the conditional expectation of U tau f, as well as the conditional variance. So now, switching gears, we will describe the multiscale test problems, which we will use to benchmark this prediction approach. We look at two classes of multiscale dynamical systems evolving on a larger state space consisting of X and Y dynamics, which are coupled in these two ways. However, we assume that we can only observe the X dynamics using KAF sampled at a macroscopic timescale in both types of systems. The first one we consider is an averaging regime, where we have the X dynamics driven by a possibly nonlinear function of X, as well as this linear term acting on the Y dynamics, which evolve on a timescale an order of magnitude faster than the X dynamics. The effect of the by term is essentially to act as an averaging term, where we can treat the X variable fixed when the scale separation is large and marginalize and integrate over the Y dynamics. So this essentially acts as an averaging term. And in this way, we can get a closure model for the X dynamics in the form of this deterministic equation where this V function is unknown. This is a standard way to model these systems in practice. However, we're going to bypass this idea by just gathering samples of the X variables and predicting the evolution forward in time without observing the Y. Now, because this closure is deterministic, this conditional expectation should simplify and remove the expectation since it is deterministic. The second type of system we'll consider is those exhibiting homogenization, which is common in molecular dynamics, for instance. And here, the Y dynamics are not influenced by the X variable, and the X dynamics are driven by a term that looks like this. The effect of this term is to essentially decorrelate in time the the quickly evolving Y dynamics. So under some assumptions on the Y dynamics, for instance, that this system is ergodic and this term is zero mean, we can get a closure of the Y forcing term and it starts to resemble Brownian motion. So the X variable has a closure that resembles a stochastic process in X. And in this case, we can analyze the KAF prediction given observations only of X, where the conditional expectation simplifies to simply an expectation of this X tau given X, which is simply the mean of the stochastic process. And this gives us a way to validate the predictions made by the KAF model. So the first one we look at is actually a homogenization example, where we try to predict the slow variable X, which is driven by a chaotic fast Lorenz 63 equation, as summarized in the previous slide. The Lorenz equations evolve on a timescale 2 orders of magnitude faster than the X dynamics, and the limiting behavior of the X dynamics is that of a stochastic process where the X dynamics are driven by Brownian motion. So given observations of x, we would like to predict x forward in time, or the conditional expectation of x forward in time. So here is a plot trajectory of the slow variable, sampled at a macroscopic timescale for small epsilon. And you can see that the effect of the y forcing term is to essentially decorrelate the y dynamics in time, and we get what essentially looks like a stochastic process. And we can compare this to the invariant distribution of the stochastic process, which we can derive analytically, given that we estimate the sigma parameter. Once we do that, we see that the histogram of the x trajectory along x trajectory is perfectly matching the invariant measure of the stochastic process. So validating our model with the stochastic process in mind is a good idea. So here is the KAF prediction of the conditional mean initialized at x equals -1. And we do a long-term forecast of the x trajectory for increasing tau for a long time duration. Now, the blue and the black and the red lines are the moments of capital X computed via Monte Carlo simulation of the SDE, roughly 10,000 realizations of this SDE on the bottom. And you can see that the predicted mean, which is the blue line, which we are calling the forecast in this figure, and the predicted conditional variance, which we use to estimate the standard deviation bands of our prediction, are matching quite closely to the mean and variance of the stochastic process, or to be more specific, the mean and standard deviation bands of the stochastic process. So this is a good validation of the methodology in the small epsilon limit. Interestingly, KAF, the variance prediction of KAF adapts to the different initial conditions that we give it. When initialized at x naught equals -1, we expect the trajectory to stay on -1 for quite a long time, based on the distribution, this bimodal distribution of the x dynamics. And hence the uncertainty of the prediction stays small. In comparison, when you initialize at x naught equals 0, the trajectory can either go positive to 1 or -1, and both are equally probable. And so the predicted variance quickly grows in comparison to the prediction initialized at -1. Now we have a look at the eigenvectors of G that we get from the KAF eigendecomposition. Remember that the eigenfunctions can be interpreted as geometric harmonics in a sense, because the operator G approximates a diffusion operator on the manifold. And we can compare the empirical eigenvectors we get from our method computed from the kernel matrix on the x variable alone to the analytical eigenfunctions that we derive from explicitly computing the eigenfunctions of the heat operator or diffusion operator of the stochastic process. And as you can see, these are these higher and higher cosine harmonic functions, and you can see that they match quite closely. Because the data and the stochastic process share the same features, we can validate the KAF prediction with the moments of the stochastic process. We now move on to an example of averaging. This is the chaotic multiscale Lorenz 96 equations, which is a network set of equations consisting of 9 slow variables xk. Each kth x variable is coupled to 8 ergodic fast variables y, in total leading to an 81-dimensional state space. However, we only observe the 9 slow variables and try to predict the first slow variable. Now, these are coupled in a way that exhibits averaging in the small epsilon limit, and the xk's satisfy a deterministic equation in terms of x alone. Now, we don't know this closure term vk of x. However, we can use KAF to predict future occurrences of xk given the data of xk from simulation. So we will study 3 parameter regimes of this equation by controlling the scalar parameter fx, which appears in the equation. So the periodic regime corresponds to a smaller value of fx, and these are phase portraits of the first 3 slow variables. An increasing fx leads to increasingly complex behavior, and as you can see in the chaotic example, it's essentially unpredictable beyond a certain time. The plots below show the effect of the y variables on the x variables. So the gray line is the averaging term of the y variables. So it is the plot of this term. So now we move on to the results of KAF. In the periodic regime, KAF essentially gives a perfect prediction with an uncertainty prediction that grows so slowly and that we cannot even see it. And we will see that in the subsequent mean squared error plots. The long-term KAF forecast converges. You can see this damping behavior in the chaotic regime. And that is because U tau f, the Koopman operator, has this property that for long tau in mixing dynamical system, U tau f is expected to converge weakly to a constant. So you can see that in the other extreme of chaotic behavior, the uncertainty starts growing, and beyond a certain time, we lose the ability to predict for a certain initial condition. And you can see this damping behavior. It somewhat stays in phase with the ground truth prediction, but it quickly, in the long term, it converges to a constant. And so this is predicted by the theory, and essentially reflects the fact that we cannot predict a chaotic dynamical system by seeing data that is further back than the Lyapunov timescale of this equation. In the quasi-periodic regime, we get a prediction that is in between, and you can see that the uncertainty is quite small throughout the prediction for from tau equals 1 to tau equals 12. And you can see that the uncertainty is largest at the extrema of the trajectory. However, this uncertainty prediction grows quite slowly as well. So we have some confidence in the prediction in the quasi-periodic regime, and nearly perfect 100% confidence in the periodic regime. Now we'd like to compare the KAF prediction with the closure model that we derive from using Gaussian process regression. The idea is to actually learn this closure term by gathering data of the xk variables and the averaging term capital YK. And you can see a plot of the fit for the regression model for VK in this plot here. The idea is that this is a model data-driven closure, so it has access to more information as well. It trains on pairs xk as well as it has access to the averages yk and learns vk. And the idea is to compare the KAF prediction initialized at a point to the closure equation with the initial condition simulated from the same initial point. So this is an illustrative comparison because the KAF, although it is perfect in the periodic case, the GPR predictions shown in the dotted line quickly becomes out of phase. And this is to be expected with such methods. I cannot maintain the perfect periodic behavior. The KAF, as we saw before, stays in phase longer in the quasi-periodic regime as well. As you can see at lead time tau equals 12, we can see that KAF, the blue line, is in phase, and GPR prediction, the model data-driven prediction, goes out of phase. The chaotic regime is more interesting. Here, the GPR prediction is better than KAF. It actually follows the trajectory up until roughly tau equals 2 for most initial conditions that we tested. And you can see this in the root mean squared error plots as well. And quickly, both of them stop being able to track the trajectory. So here are the root mean squared error plots across roughly 3,000 initial conditions. So we do a systematic comparison of 4 different cases where the first one, the blue line, is the standard KAF. We try to see if the KAF prediction is better when you augment the observations by the averages of the YK variables that are involved in the closure term. And we expect that this won't help much because the closure is in terms of the X variables. And that is what we see reflected in the plot. So the A and B lines do not display much improvement over the A line. Observing YK does not really help when the model is deterministic and depends only on the XK, which is what we expected. The GPR prediction does poorly in the periodic regime and improves in the quasi-periodic and chaotic regime. However, it does not have this property that it converges to a constant, so the error keeps growing beyond the KAF predictions in the chaotic regimes. And finally, we essentially validate KAF by training it on the data generated by the closure model, and we can see that it has similar performance in the chaotic case, which validates the GPR model as a valid closure model for the Lorenz 96 equations. And in the other cases, you can see that KAF in case D does essentially just as well or just as poorly as the GPR closure model. So we've tested 4 different classes of multiscale regimes, periodic in the slow variable, quasi-periodic, chaotic, as well as roughly stochastic. And you can see we have studied different behaviors that we can expect with the KAF predictor when using partial observations. So this provides a way to validate the forecast that we can expect when we don't know the equations. We only observe partial dynamics, and we would like to get an estimate of the confidence associated with our prediction. And this is especially useful in these deterministic systems. For a point of comparison, we also run KAF where the closure in terms of X is not Markovian. That means for large epsilon. So the coupling between the X and Y is strong, and you cannot hope to predict the X variable without observing the Y. And in both cases, in the homogenized equations, the Lorenz 63 forcing the x variable, the uncertainty quickly grows. So we can see that we are missing some important information needed to predict the x variable. And when we in this case, we needed to, in order to get at least a little bit of prediction accuracy in the short term, we actually augmented the observations by the driving term in the y dynamics, and you can see that we are able to predict very closely for a short term, but then quickly we lose prediction ability. We can observe the same phenomenon in the Lorenz 96 equation, where we quickly lose the trajectory and the uncertainty quickly grows, and we cannot track the trajectory even for tau equals 2. So just to quickly summarize, KAF gives a systematic way to analyze the predictions when you have partial observations of a dynamical system. It displays long-term prediction accuracy for certain classes of multiscale systems. And it has this very useful conditional expectation or operator theoretic interpretation for dynamical systems, and in this case, multiscale dynamical systems. And this is important when you would like to say something about the underlying dynamical systems when you don't have access to equations or the larger state space. One very useful consequence of KAF is the variance prediction, which encodes the information loss you get from partial observations. And you can see that the predicted variance adapts to how much information you have, giving you an indication of whether you have even observed enough to be able to predict forward in time. So this work brings up some useful future directions and questions, including how to use this prediction methodology for data assimilation for more large scale systems in climate and ocean sciences. And we would also like to improve this methodology using delay embeddings, which are a common way to augment the observations by time-shifted copies of the observations. This is a consequence of Tuckin's theorem that this helps mitigate the information loss from partial observations of a system. And this is seen all over the Koopman data-driven analysis work. And another final thing we would like to look at, which I haven't mentioned here, is the ability to predict vector-valued observables. And this is important when you want to predict fields or velocity fields and don't want to compute a predictor for each different coordinate. So this is a very useful methodology, and there are several ways we can think of to improve it and investigate further. Thank you for watching.